Hey everyone, it's Emily, and this video is all about the basics of linear regression. Y equals mx plus b is linear regression in its most basic form, and we're going to talk about how we relate our independent variables to dependent variables. How does an increase in one variable correlate, not cause, but correlate with a change in another variable? We're going to talk about how to look at these concepts visually with scatter plots, using R and R squared values, and then using basic word problems to put together simple bivariate or two-variable linear regressions. Then I'll also show you the basics of understanding what a linear regression looks like in Stata, our statistical program. Loving the birds outside. Looking at how we interpret the results that come back from the program and report them in a scientific way. So let's get started. Let's start with scatter plots. Scatter plots are points of data in which each individual point represents a relationship between an x variable and a y variable. And as you can see here, we've got a joke. I don't trust linear regressions when it's harder to guess the direction of the correlation from the scatter plot than to find new constellations on it. Rex Thor, the dog bearer. What is a scatter plot? Scatter plots are so useful because they can help us visually see relationships very quickly between x and y variables. They can be used to visually determine the strength of a relationship between an independent, or x variable, and dependent, or y variable. The value of the y, or dependent variable, for each value of the x, or independent variable, will be plotted as a single point, as shown here on this chart. The scatter plot on the left shows a very strong relationship between two interval or ratio variables. You see how we could estimate a line going along our points, and that all of these scatter plot points seem to hang really closely, really tightly to this point. If I had asked you to estimate your own line, you probably would have come up with the same kind of best fitting line, drawn straight through, rising from the left to the right, so a positive line that increases as you go from left to right. And again, each dot in the scatter plot here represents a value of the y variable at the given value of x. So for example, I'm estimating here for this point. So an x value of about 38-ish, and it has a y value of, and we go across to the y-axis to determine, looks about to be 250. So at each of these points, there is this distinct and single value of x and y that intersect at that. Let's look at an example of how we might plot data independently ourselves. Amelia in this example plays basketball for her high school. She wants to improve to play at the college level. She notices that the number of points she scores in a game goes up in response to the number of hours she practices her jump shot each week. Right? Practice makes perfect. This is a really simple problem. Here's how she's recorded the following data. She notices that when she practices for more hours before a game, she tends to score more points in that game after. See how as x values seem to increase from 5 through 9 through 12, the points for y, which are points scored in a game, seem to also increase, right? From 15, 28, 36. Here we have the same table, just squished a little differently so we can see everything on this slide. Here's how we've plotted out that data. Again, this might be a review for you, but it's good to make sure you can build your own scatter plot by hand. What we've done is taken our independent variable, or our x variable, hours spent practicing a jump shot. We don't know that hours spent practicing a jump shot fully causes the number of points scored. There are lots of different factors, such as injuries or different teammates, different game circumstances that might influence how many points that Amelia scores. It's not just how many hours she spent practicing a jump shot. And then each of these points here is at an intersection between one x and one y value. So when x was 5, Amelia's points scored in that game were 15. When x was 7, you can see we've gone up from 7 to where 22 lies on the y-axis, and we've put a point here. We've continued with all of those points. Do you think that there is a linear or straight line relationship that we can draw between all of these points? Of course, because it's a practice problem, this looks to be extremely linear, right? I could almost perfectly draw a straight line through all of the points, maybe with a little bit of error, right? But we can really see there seems to be strong positive relationship between the independent and dependent variables. So what we're looking at here is a strong positive relationship. And honestly, it looks pretty perfect, maybe too perfect. So the example on the previous slide shows a strong positive relationship between the independent and dependent variables. This is a clear positive relationship. As x increases, y also increases. The direction of a relationship, when clear, can be either positive or negative. High values of one variable occurring with high values of another variable indicates that positive relationship. So sometimes we say positive, sometimes we also say a direct relationship. High values of one variable occurring with low values of the other variable indicates a negative relationship. And sometimes we say that this is an indirect relationship. You can determine the strength of a relationship in a scatter plot by how closely the points on the plot stick together in that linear form. A relationship on a scatter plot is strong if there's a clear pattern in one direction, except if the line is horizontal. Let's talk about what scatter plots look like in Stata. You'll see that relationships between variables in Stata are rarely as strongly related as in the examples we've shown so far. Even when they are, the pattern might not be as easy to discern visually. On the next slide is an example from the American National Election Survey from 2016. The independent variable is feelings towards the Republican Party on a scale from 0 to 100, where 0 is very negative, a negative feeling towards the Republican Party, and 100 is very positive, a positive feeling towards the Republican Party. And then the dependent variable is feelings towards Donald Trump, again on the same scale. All right, so this is what the scatter plot looks like when we show all of these thousands of data points on one small graph. You can kind of maybe see that there are clustering of points here in the center of the graph, and I've drawn a line here that might approximate a positive relationship. What we know from living in our social lives is that feelings towards political candidates doesn't always align with feelings towards the political party that they represent. But we would expect that generally, folks that feel positively about a political candidate might also feel positively about the political party they represent. But again, that correlation in society is not perfect. However, we can determine that because the points seem to cluster together at 20 and 20 and 40 and 40 and so on, that there is some relationship. It's just not a strong relationship as noted in earlier examples. We can tell that this because we see a lot of spread of the data. The points are spread apart and not very close to this line that we've added to our graph. So what about a scatter plot where there is no clear pattern, right? Notice that this plot looks like spilled marbles or just random dots on the page. Here we're looking at a relationship or maybe a lack thereof between length of time living in a community and whether that predicts a respondent's feelings towards Trump. I'm having a hard time figuring out whether this would be a positive or negative relationship, at least visually. What we'd need to do is run some statistical programming to really see mathematically what's happening on the page. Let's make sense of this by using a more concrete mathematical concept called R, the correlation coefficient. We will use correlation coefficients to calculate the slope in linear regression, but also to determine the strength of a relationship between x and y. The correlation coefficient, also noted by a lowercase r, was developed by Carl Pearson in the early 1900s. It's numerical, and it provides a measure of strength, 1, and direction, 2, of the linear association between the independent variable x and the dependent variable y. Your textbook provides a long and drawn-out formula for finding R. In this course, we will not need this formula, and I'll tell you, in the real world, I never calculate R on my own. That's something that I get when I work with my statistical program to figure out the strength of a correlation. So let's review, what is correlation? And I know you've heard it a million times. Correlation does not equal causation, and we want to make sure we're really specific when talking about bivariate regression. Correlation is a statistical technique that can be used to describe a relationship between two variables. If you want to see if there's a correlation between two variables using correlation coefficients, they need to be interval or ratio variables. First, let's talk about positive correlation. If values go up in one variable, values should also tend to go up in the other variable. So if I plotted a positive correlation, I would expect to draw a best fit line that goes up from left to right. Now let's talk about negative correlation. If values go up in one variable, then the values tend to go down in the other variable. Again, if I drew this out, I would expect a negative correlation to have a best fit line that went down as I went from left to right. I've drawn this number line for you as I think it helps summarize all of this information. Take a screenshot and use this as you go through your practice problems. So here I've drawn a number line. R can only have values between -1 and 1. So if your R equals 0, there's absolutely no correlation. It might as well look like, as we talked about before, spilled marbles on your scatter plot. You can't make sense of whether there is a relationship between your two variables in any direction. If you have an R equals 1, that's a perfect positive correlation. Every single point perfectly fits mathematically onto the best fit line. There are no errors. If your R equals -1, you would expect a perfect negative correlation. Again, all of the points of your scatter plot would fit perfectly on your line. Now let's review, what do we expect in terms of the direction of the line? If you have a positive R value, you're looking for any value that's between 0 and 1, right? Mathematically, any value above 0 is positive. And as x increases, y increases. So again, just to draw, you would expect a best fit line going up from left to right in this direction. A negative R value, again, this is just by mathematical definition, any value between -1 and 0 is negative. And we would see on a graph that as x increases, y decreases. So we would expect a best fitting line that goes down from left to right. So we know in real life, in our social world, things are rarely mathematically perfect. We rarely see a perfect positive or perfect no correlation or perfect negative correlation. Instead, we tend to see values that are very close to 0 or 1. So if I had a value of R equals, say, 0.8, that's a strong correlation. It's close to 1. I would expect that most points are close to the line, but we might have a few outliers here or there. That would best approximate an R value of 0.8. What about a strong correlation that's negative? That would be something like -0.8, -0.7, right? I would again expect that the points would hang close to my best fitting line, but they wouldn't all perfectly lay on that line. What would a weak correlation look like that's positive? I would say maybe an R value of 0.2, something that's between 0 and 0.5. And I would expect maybe we have points that seem to go up from left to right, but they wouldn't perfectly lie close to a line. There looks to be a positive correlation, but it's not very strong. Similarly, if I had R equals -0.2, I would expect again a cluster of dots that seem to go down, but they don't all align perfectly on that line. In this example, our x variable is temperature in degrees in Fahrenheit. And then we're looking at the relationship between beer sales and temperature. Does the outdoor temperature fully cause beer sales? Of course not. It's one of many factors in life that might contribute to aggregate beer sales, right? But we might think, well, as the weather gets warmer, maybe we spend more time socially outside or in public spaces with our friends, so we might expect there to be more beer sales as the temperature increases. Here you can see that there is a positive correlation. These dots are not close to the line, but you can see as the temperature is low, these points of beer sales tend to be low. As the temperature is high, the beer sales tend to be higher points. So again, as X increases, it looks like Y increases, so our R squared value will be positive between 0 and 1. If I had to estimate, I would say that this is, not especially strong. I would say it's a mid-range R value. I would say this is about 0.4. Again, we're not mathematically computing that value right now, and this is just a sample problem. But if I asked you a multiple choice question, you would want to select an answer that's not a perfect 1 or -1, right? Because we don't see all of the points aren't lying on the line. And you would want to pick something mid-range, right? It's imperfect, so it should be positive, but somewhere in the middle. Again, let's look here. So this one looks at the relationship between coffee sales and temperature. Now, I'm a caffeine addict, so I'm always buying coffee regardless of the temperature. But in this example problem, we can see that as the temperature is low, we see the amount of coffee sold is high. But as that temperature increases in degrees, it seems like there are lower sales of coffee. Again, this must be wrong. They're not including cold brew. But for this practice problem's purposes, we can see that there is an indirect relationship or a negative relationship between X and Y. So if I asked you the correlation coefficient, or what is R, would it be positive or negative? Well, since this is a negative line, this is a negative relationship, we would expect a negative value. Is it perfect? Should we say R is -1 exactly? No, again, you can see that there are a lot of dots that don't come very close to the line. We just see that there's a general trend. I'm estimating that maybe our R value is -0.4 or 0.5. Somewhere in the middle. It's not especially weak, it's not especially strong. Let's look at some other R squared values. It's good to just practice visually assessing a scatter plot and determining what your R value should be. Here, your textbook suggests that because we can draw a tight circle around our points, that we would have a high positive R value, something like 0.9 or 0.8, because I could draw a best fitting line that maybe perfectly goes across several of the points, with small errors between other points. Here is an example of one that is a little harder to determine. If I drew a circle around all these points, you can see maybe it's oblong, it's an oval, it's kind of tilted in this direction, but we have a lot of points that don't perfectly map onto our line. So it's a negative value because it's a negative correlation, and we could put the correlation coefficient somewhere in the middle. Not super weak, not super strong, so 0.4 or 0.5. Here is a perfect negative correlation. See how every dot perfectly lies on one straight line that's decreasing as X values increase, the Y values decrease? So R is -1 exactly in this case. Here, and I agree with the textbook, I have no idea in this example whether there's a positive or negative relationship. It looks like spilled marbles, it looks like random granules of sugar. I can't determine whether there's a positive or negative relationship. Maybe you might see one, but I could just as easily draw a line this way as this way and feel like it maybe fits the data. In this case, R is 0, we're saying we don't see any correlation between our x values and our y values. Let's talk a little bit about interpreting correlations. The first important point, and I know I'm sounding like a broken record, is that correlations describe a relationship between two variables, but they do not demonstrate causation. So we can talk about correlation and we can talk about relationships, but we can't necessarily say that there's a causal relationship between two variables. So here's an example. Neighbors with many churches tend to have higher crime rates, but that doesn't necessarily mean that churches contribute to crimes, right? What we know socially is that neighborhoods that have many churches often have more people that can go to those churches, meaning that there would be a higher incidence of crime. So it might be a contributing factor or a predictor of another variable, but we can say there's a relationship, but we can't say that there's causation between these two variables. Correlations describe relationships in observed ranges of x values. You always have to think, well, what am I missing on my x or y scale? Let's look at this, for example. First, let's look at the overall trend, ignoring this dotted line. Do you see how as x increases, y also increases? I would probably draw a line like this, right? However, let's say we only observed x values in this upper range, and we only observed the values of x between here and here. When I look at these points, as you can see, we've drawn a circle around these points. I can't tell if there's a positive or negative correlation. So it's hard to determine an actual relationship. Again, let's look at this example. If I looked at the big picture with all x values included, I don't really see a big trend here. It's hard to determine the direction. But if I got rid of these points, meaning that I didn't observe x values between here and here, and I just look at these limited values, to me that looks like a very clear positive relationship. Number 3, outliers can affect the correlation dramatically. First, look at this chart. I'm not really seeing any relationship here, and the value of r is very close to 0. However, if I included an outlier here, where x equals 14 and y equals 12, that severely changes the directionality of the relationship between x and y. Just including that one point alone increases our r value from almost 0 to almost 1. Squaring the r value, the correlation coefficient squared, allows us to say how much of the variation in our data is explained by our linear model. So let's say we have an r value, a correlation coefficient of 0.8. Remember, it has to be between -1 and 1. And if we had an r value of 0.8, that's a pretty strong positive relationship. How much of our variation in our data is explained by our linear model? All we have to do is square the r value and report it as a percent. 0.8 times 0.8 is 0.64. Convert that to a percent. If we have a correlation coefficient of 0.8, that means our r squared value is 0.64 or 64%. So we can say a full sentence that 64% of the variation in our data is explained by our linear model. That's a pretty high percentage. So when I look at my r squared value and I see about 0.64 or 64%, I think my model is doing a pretty good job of understanding this relationship. Let's talk more specifically about what linear regression is. Being able to do linear regressions in your head is cool, but it has its drawbacks, like knowing 3 weeks in advance the moment she will send the final text. Time, number of texts received. Fun joke. You can think of regression as an extension of correlation. Like correlation, regression can be used to describe a relationship between 2 or more variables. But let's focus on 2. With regression, you can predict a value in the outcome variable from the predictor. The overall idea of regression is to examine 2 things. 1, does a set of predictor or independent variables do a good job in predicting an outcome or dependent variable? And then 2, which variables in particular are significant predictors of the outcome variable? In what way do they impact the outcome variable? These regression estimates are used to explain the relationship between one dependent variable, must be interval or ratio level variables, and one or more independent variables. The simplest form of the regression equation with one dependent and one independent variable is defined by the formula y equals mx plus b. It might look familiar. Y is the estimated dependent variable score. B is the intercept or the constant. M is the slope, and x is the score on the independent variable. Your text notes the linear equation as y equals a plus bx. Again, it's the same formula as y equals mx plus b. We're going to stick to using these symbols for consistency. It's the formula that most people have learned in high school, and you might be more familiar with this equation. So, B is your y-intercept. This is where the line crosses the y-axis, the axis that goes up and down vertically. M is your slope of the line. No matter what letters are used, the formula for a line is as follows. Estimated dependent variable value is equal to the slope times the value of x plus your intercept value. The graph of a linear equation of the form y equals mx plus b is a straight line. We're only going to talk about regression using straight lines in this course. Any line that is not vertical, perfectly vertical, straight up and down, can be described by this equation. Remember that the slope is a number that describes the steepness of a line, which is the increase vertically divided by the increase horizontally. The y-intercept is the y-coordinate of the point 0, a, where the line touches the y-axis. Here's what that looks like visually. The equation associated with our line is y equals mx plus b. Here we can see that the slope is positive, so as the line goes up from left to right. We can see our y-intercept is b here. It's the point where our line crosses the y-axis. And the slope, m, is what determines the steepness. Let's look at an example that mirrors what you might see on an exam in this course. Aaron's word processing service, AWPS, does word processing. The rate for services is $32 per hour plus a one-time $31.50 charge. So the total cost to a customer depends on the number of hours it takes to complete the job. Find the equation that expresses the total cost in terms of the number of hours required to complete the job. Okay, first let's identify the dependent variable. The dependent variable, the question we want to answer is, what's the cost? So what's the total cost that's billed to our customer? Next, let's identify the intercept. It doesn't matter how many hours that Aaron works to word process. We know that there's a fee. When x equals 0, when the number of hours equals 0, we still have this payment. We can see that there's a $31.50 one-time charge, that this charge isn't dependent upon how many hours Aaron works. So we know that Aaron will make $31.50 as a one-time charge even if it takes less than 1 hour to complete the job. That's our intercept. Then we'll find the slope. This is the amount per hour that Aaron will make. The slope is generally noted as a value per unit. So here we can see that he makes $32 per hour. $32 per hour. The only variable left is x, which is hours worked. If we put this all together, we would say y equals mx plus b, which is like saying the total cost is $32 per hour plus the one-time fee, which is $31.50. We can use this equation to then predict how much it would cost if Aaron had to spend a specific number of hours. Let's look at another example. Svetlana tutors to make extra money for college. For each tutoring session, she charges a one-time fee of $25, plus she charges $15 per hour of tutoring. A linear equation that expresses the total amount of money Svetlana earns for each session she tutors is the total amount, y, equals 25, that one-time payment, which is like b, y equals b, plus mx, our slope, times our x variable. Here we're saying $15 per hour. So our slope, or our steepness, is 15. What are the independent and dependent variables? Let's write that out. X is our independent variable, and it's the number of hours worked. Y is our dependent variable, and it's the total cost billed to the client. The y-intercept is B, and that's our one-time fee. That doesn't depend on how many hours Svetlana works. Finally, the slope is the steepness of our line, and we would write that as m. Sometimes we say slope, sometimes we also say coefficient. Fancier statistical word, means the same thing as slope. And here, this is the dollar amount per hour of tutoring. So in this case, it's 15. Now, what would happen if I asked you to use this equation to figure out total cost? Let's say that Svetlana worked for 3 hours. If x equals 3, what is y? All I have to do is plug into the equation. Y equals b, that doesn't change, 25, plus my m, my slope, or coefficient, is 15. And here I plug in x, which is 3. Y equals 25 plus 45. Y equals $70. See how that works? Let's briefly talk about what linear associations and regression looks like in Stata. So look at this example. When running a scatter plot for the number of kids respondents have based on their education level, it wasn't very clear what the pattern was, although the number of kids respondents have seemed to go down on average with each additional year of education. To take a better look, I used the ordinal measure of education to compute a mean number of kids at each level of education. As highest level of education attained increases, it seems like the average number of kids goes down. What kind of relationship is that? As education increases, the average number of kids goes down. So we would expect a negative relationship that goes down from left to right. We can surmise that there's very likely a negative correlation between education and the number of kids people have. We will determine if there is a true linear relationship between these variables using the regress command in Stata. That's going to be covered in a few slides. First, let's talk about the regression line. It's the best fitting line for our data. So we visually have determined lines that best fit our data just by slashing a line through it visually. But regression lines are calculated using a pretty precise series that reduces this total squared distance between points. For a given data set, you can draw many lines, but the regression is said to be the best fitting line. What do we mean by this concept of best fitting? We define it in a specific way. We draw a line, and then we look at the vertical distance between each point and the line. So some points will be above the line, some points will be below the line, but we measure these small distances between each point and the line we draw. So that's like saying we take an observed value, our point, and we see what the predicted value would be, which would be the point that lies perfectly on the line. We say that this distance here is an error. So what we do is we add up all these errors and we square them. We take these distances, we square them, and add them all together. Mathematically, we say the best fitting line minimizes the value of total squared distance. I know this might take a little bit of time to sink in, but just really focus on this definition for your upcoming exam. We want to minimize the value of total squared differences between observed and predicted values. Remember, data rarely fit in a straight line exactly. Usually you must be satisfied with rough predictions in statistics. It's a way of life. Typically you have a set of data whose scatter plots appear to fit a straight line. This is called a line of best fit, or an ordinary least squares line. The cool kids call it OLS. We will use this least squares regression line to predict those values of y for values of x. To do this, we have to find the slope and the intercept, and the line will always pass through the mean of x and the mean of y. Finding this line, the least squares line or the best fit line, is exactly what we're doing when we run a linear regression. Although it's simple to find the slope of a line generally, its general steepness, finding the slope in a linear regression equation is quite different. We're still looking at the changes in y as a result of the changes in x. The formula for the slope in linear regression lines is a little bit different. Here's information that will always be provided to you. You can see that there are formulas for the slope in your textbook that are essentially the same. However, for the purposes of your exam, you will be given the slope and asked to interpret. So you will be given that slope or coefficient value from Stata, and you will be expected to report this sentence. For a 1-unit increase in the x variable, the value of the y variable increases by, and here's where you put in your coefficient or slope, blank units on average. Remember, the intercept value will be the value of y when x equals 0. To find the intercept, we simply use our regression formula and we enter in 0 for x. In Stata, the intercept will also be provided to you. It's shown in the regression as a constant or underscore cons. Here you can see that we had an observed value that when x equals 5, y equals about 7. That was our observed plot point. However, we want to know what the predicted y value is. All we have to do is plug into our formula. Here, our best fit line is that y equals 1.6x minus 2. So here, I will just put in the value for x equals 5. 1.6 times 5 minus 2 is 6. So you can see that the predicted y value, which is here on the line, is 6. And that there is an error, which we would expect, between the observed value and the predicted value. Let's go back to looking at the relationship between number of kids and years of education. Here we're using Stata and we've entered regress, our dependent variable, number of kids, and independent variable, years of education completed. This big square table is what's produced by Stata when you enter the regress command. Over here in the upper right-hand corner, we have a lot of facts that are useful. The number of observations, here we can see that 9,903 respondents are included in this data. We can also see an r-squared value. Remember, r-squared tells us how much of the variation in our data is explained by this model. Turn this value into a percent. It looks like 3% of the variation in number of kids is explained by years of education. So maybe it's not a very strong relationship. So these are pieces of information I expect you to be able to report on. R-squared values and numbers of observations. Up here is information that's used to conduct OLS. I'm not going to ask you in this course to interpret this information. What I want you to do is to go to the table that's at the bottom of your regression results. Here, you can see your education variable. That's the years of education that an individual has. And you see in this first column, COEF, which stands for coefficient or slope. So what you'll want to do is look at this coefficient. This is your m in your y equals mx plus b calculation. What's nice about regression is that we can also see if there is a statistical significance to this correlation. What we do is skip over a few lines to this column, the probability column. Here you can see that this number, 0.000, is less than 0.05. So we can say that there is a statistically significant relationship happening here. Now we found our coefficient m, but we're looking for our intercept value b. That's our constant value. It's what y equals when x equals 0. Here we just look for cons, which means constant value, or b. Here you can see that b is 1.85. So if I had to write my regression equation using this information, I would say y, which equals number of kids, is equal to m negative 0.0, rounding, 5 years of education is x plus 1.85. If the respondent has 0 years of education, the predicted value would be that the respondent had about 1.85 kids. And then as x increases, we would expect a small deduction in number of kids on average that person would have. This follows what we saw in the data earlier, that as education increases, on average, respondents have fewer kids. And again, we can say that because of this value here, that this is a statistically significant relationship, even though it has a very small slope or coefficient, it still seems to be a significant one. Let's look at one more regression interpretation example. Here, we're seeing if our dependent variable, cholesterol, this is interesting. Would you say that watching TV causes cholesterol changes? Well, definitely not fully. Watching TV doesn't cause the levels of your blood cholesterol to increase. However, we know as social scientists, there are a lot of factors that are associated with watching TV. People tend to generally eat more junk food snacks while watching TV, or they might have less time to exercise or engage in other activities. So there might be a correlation between watching more TV and other health habits that could influence cholesterol. So again, we're not saying that hours watching TV causes cholesterol changes, but there might be a correlation or a relationship between the two. All right, so we've run this data output by just typing these 3 words, hitting enter, and here's what comes back. Again, this information we don't need to worry about for the purposes of our course, but it's what's used to calculate the best fitting line. We can start here in the upper right-hand corner. How many observations were in this data set? Or in other words, how many people were included in this survey? Yes, n equals 100. Now, what's the r squared value? Here, you can see it's 0.15. Let's convert it to a percentage, 15%. What we can say is that 15% of the variation is explained by our model. Not a lot, but it's definitely something to investigate. All right, let's look at the slope. Where would we find the slope? Well, we find our independent variable, time TV, here in this column, and then we go to the right to the coefficient column. Here, you can see the coefficient is 0.04. Is it a statistically significant relationship? If I keep going over to the probability column, yes, it's 0.000. What we can say in a sentence is that this is a statistically significant relationship because the p-value is less than 0.05. I erased the circle so we can read. What is our intercept value? It's also known as the constant. So we find constant in this column and we go 1 column over to the right. We can see that our constant value is negative 2.13. This is like saying cholesterol equals 0.04 times hours watched of TV plus, and now we have a negative intercept, so plus negative 2.13. And we can simplify that by just saying minus 2.13. So now let's think about this. Can you have a negative cholesterol reading? To be frank, I don't think so, but I'm not a doctor. I would say that this doesn't necessarily have mathematical meaning. However, it just so happens to work out with our best fitting line. Sometimes, as we've seen in our tutoring problems that we looked at earlier in this video, our intercept has an actual meaning, like a one-time payment or a minimum salary requirement, some kind of minimum when our x equals 0. Sometimes it's just the mathematical luck of the draw. So what we would do if we wanted to figure out somebody's cholesterol score is insert here the number of hours of TV they watch, multiply it by 0.04, and then subtract our intercept value, 2.13. Again, we're subtracting this value because it's a negative intercept. So it's really like adding a negative intercept. This is a statistically significant relationship, but remember, this is a very small number. So it looks like the number of hours watching TV can contribute to a cholesterol score increase, but it would take many hours of TV to have a significant increase on your cholesterol. Before I sign off on this video, here are expectations for what you should be able to do for exam 6 in this course. Scatterplots. Can you visually interpret a scatterplot to determine an approximate value of R, your correlation coefficient? Remember the simplest form of linear regression. You want to make sure that you can work with this equation and construct this equation given a word problem. You would also want to make sure that you could take the information, plug it into the equation, and derive estimated Y values for given X values. You'll want to interpret linear regression results using this sentence. For a 1 unit increase in the X variable, the value of a Y variable increases by blank units on average. You'll want to interpret R squared on this exam, and if you're given R, all you have to do is square it to get R squared. Turn that proportion into a percent, and then explain it by saying the X variable explains 45% of the variation in the Y variable. And you'll want to practice a little bit with interpreting regression results from Stata. Can you identify the constant or the intercept B, the coefficient slope M, the number of observations N, find R squared in the upper right-hand corner, and interpret the p-value? Can you determine whether this is a direct or indirect relationship? Of course, by looking at the positive or negative sign next to M, your slope. Here are the top 3 takeaways from this video. I want you to master the meaning of R and R squared values and how to interpret them. And I think that this chart especially will be helpful for you as you work through practice problems. You want to practice with example problems to make sure you understand how to interpret simple bivariate regression. Bivariate regression is that fancy way of saying y equals mx plus b. And then you want to practice finding key details in your Stata results and report them in full sentences. So making sure you can find the information in this regression results table and report it out correctly. All right, thanks everyone. Have a good week.